All right, welcome. Today we are going to pull back the curtain on machine learning and see exactly how computers learn to predict things. It's a fascinating world, so let's just dive right in. You ever wonder about that? How can some app on your phone look at a few pictures of a house and spit out a pretty accurate price? Or how does your email somehow just know what's junk before you even see it? It feels kind of like magic, doesn't it? But you guessed it, it's not magic at all. It's actually a set of really powerful thinking tools, or you can think of them like recipes. We call them algorithms. And these are the secret sauce, the engines that let a machine learn from experience and make those incredibly smart guesses we rely on every single day. Okay, so let's start with our first challenge, teaching a machine to predict a specific number. In the world of machine learning, this is a core task, and it's something called regression. So imagine we want to predict the price of a used car. The first thing we'd do is collect a bunch of data. We'd plot out each car's mileage against its selling price, just like you see here. See all those dots? Each one is a car. The machine's job is to stare at this cloud of dots and figure out, is there a pattern here? For a job like this, we'd pull out a tool called linear regression. And its goal is surprisingly simple. Just draw the best possible straight line right through the middle of all that data. Now, why a straight line? Well, because it's the simplest way to represent a relationship. And that one line, that becomes our model. It's the machine's own little formula for how mileage affects price. So what makes a line the best one? It's all about how wrong it is. You want to minimize the error. A good model, like our happy friend on the left, has a line that's really snuggled up close to the actual data points. The errors, those little red lines, are tiny. But a bad model, on the right, well, its line is way off, and the errors are huge. The machine's goal is to be that happy face on the left. Okay, so that's the big question, right? How does a machine actually know which line is the best? I mean, it can't just eyeball it like we can. It needs a way to measure its own performance, and it needs to do it with math. And the answer is something called a cost function. Honestly, the best way to think about it is like this. It's how the machine grades its own homework. For any line it tries to draw, the cost function calculates a single score that represents the total amount of error. And the goal? It's simple. Get the lowest score you possibly can. Whoa, okay, I know this formula looks a little intimidating. Don't worry about the symbols. The concept, the idea behind it, is actually really simple. All it's doing is this. For every single dot, it measures the distance up or down to the line. It squares that little distance, and then it just adds all of them up. That final number, that's the cost. That's the total error score for the line. So how does it find the line with the absolute lowest cost? It uses this really clever process called gradient descent. Imagine you're standing on the side of a big hilly valley, but it's totally foggy. You want to get to the very bottom, right? What would you do? You'd probably feel the ground beneath your feet, find which way is steepest downhill, and take a step. And you just keep doing that step by step until you couldn't go down anymore. That's exactly what gradient descent does. And you can literally see that downhill walk happening right here. Each of these lines is one of those steps the algorithm takes. It starts with a pretty random guess, and with every single step, it adjusts the line just a little bit, getting closer and closer and closer to that one perfect line that has the lowest possible error. All right, so predicting a number. Check. We've got that. But what happens when the answer isn't a number at all? What if it's just a category? Like a simple yes or a no? This is a whole different type of problem, and it's called classification. See, the whole question we're asking changes. Predicting a car's price could be any number, 30,000, 4,500. But deciding if an email is spam, that's a choice between two specific labels, spam or not spam. It's a yes or no situation. For this kind of job, we need a different tool. It's called logistic regression. Now, don't let the name fool you. Even though it has regression in it, it's for classification. Instead of fitting a line through the data, its job is to find the best line to separate the two categories. That line becomes a decision boundary. It helps the machine decide if a new email lands on the spam side of the line or the not spam side. Okay, this last approach we're going to look at is maybe the most intuitive one of all. Let's see how a machine can make a really good guess just by looking at what's around it, by checking out its neighbors. Let's try a little analogy. Imagine you're out hiking. Your friend has already told you that 30 degrees Celsius feels hot to them, and 10 degrees feels cold. Simple enough. Then you stop for a break, and the thermometer reads 15 degrees. What would you guess your friend would call it? You'd say cold, right?
Of course you would. And why? Because 15 degrees is just way closer to the cold example of 10 degrees than it is to the hot example of 30. You just used simple closeness or proximity to make a really good guess.
And boom, just like that, you've completely understood our next algorithm. It's called K-nearest neighbors, or KNN, and it works exactly like our mountain guess. To figure out what a new unknown data point is, it just looks at its closest K neighbors. Maybe its 3 closest neighbors or its 5 closest neighbors, and it holds a vote. If most of the neighbors are blue, it guesses blue. It's really that simple, but it's incredibly powerful.
So there you have it. We've seen 3 different ways a machine can think: by drawing a line, by creating a boundary, or by asking its neighbors. And here's the best part. These aren't just abstract theoretical ideas. They are real, practical tools that you can use. And here's the really cool part. You don't have to be some math genius and build these algorithms from scratch. They already exist, all wrapped up inside powerful software libraries that are completely free and open source for anyone to download and use. The main toolbox, the big one, is a library called Scikit-learn. It has all the algorithms we've talked about today, plus a ton more. It's built on top of another library called NumPy, which is like a super fast calculator that handles all the heavy-duty math that makes the stuff work. And to round out the toolkit, you have things like Pandas, which is amazing for loading and organizing all your data, and Matplotlib, which is the tool that lets you create all the awesome charts and graphs we've been looking at, so you can actually see what your data is doing. So let's just sum it all up. At its heart, machine learning is just about using these clever algorithms to find patterns in data. We saw how linear regression predicts a number, we saw how logistic regression makes a yes or no choice, and we saw how KNN just guesses based on what's nearby. And the most important thing to remember? These incredible tools are out there, and they're accessible to everyone. So we've peeked behind the curtain and seen a few of the core ways machines actually learn. And I'll leave you with this question. Now that you have a sense of how machines think, what's the first problem you would want to teach one to solve? Thanks for watching.